Hey everyone, in this video we want to solve problem 1136, parallel courses using DFS and caching. So the problem is we are given an integer n which represents the number of courses, and we have n nodes labeled from 1 to n, which each of them represents a course. And we are also given an array of relations in format previous course and next course, which defines the edges, which represent the prerequisite relation between courses previous course and the next course. And in each semester, we can take as many courses as we want, but we cannot take any courses that are prerequisites in. There is a prerequisite relationship between either of them. So for example, here in this example, we can take in one semester, in semester 1, both course 1 and 2, but you cannot take 3 as 3 needs requirement to pass courses 1 and 2 in the previous semester. As another example, so let me define an example myself. So if we have courses like this, it will take 3 semesters to pass this course requirement. So 1, 2, and 3. In some cases, as this, for example, as this example here, this directed graph could have a cycle. So in case of cycle, we should return a -1 because there is no way that we can satisfy a course by passing the requirements or prerequisite of that course in the previous semesters, because we have a cycle and we should return -1. So this problem, I want to solve this problem or see it as a longest path in a directed graph. For example, in another example I illustrated a few minutes ago, so here we can consider this problem as simply as finding the longest path. For example, here, this is the only thing that matters. So this path is the longest one by 1, 2, 3, and 4. But this one, if we start from this node, so it will be 2 or 3 if we count, so it would be 1, 2, 3. So here, the only thing that we need to find is to, if we start from any node, what is the longest path we can end up by starting from that specific node. So first of all, we are given in relations, but we need to store this information of the graph in some other format. For this problem, I would rather to store it in a adjacent list format. So I would define a default tick of list. So let me import from collections default tick, and then for each previous course and the next course in relations, the graph of previous course to depend the next course. What's happening here is that, so for each node in this example here, so we have 1, 2, and 3, we are storing all HSN or all the next courses that does have an edge from that course or that node in a list. So for 1, we have 3. For 2, we have 3 as well. But for 3, we have an empty list. What I would like to do is that these courses are 1 based, so starting from 1 to n. So for simplicity that we want to use in Python, so let's map it into a 0 based. So I subtract 1 from each of them. So now we have the graph. And in order to find the longest path, one way is we can start a DFS from any node, so iterating through all n nodes from 1, 2, and 3, and run the DFS and see what is the longest path or how many iterations, what is the maximum depth of DFS starting from each node separately, and then keep track of the maximum and return it as the maximum value. And we will discuss how to find the loop in that after that. But in order to speed up the process, so let's say here, we don't know the order of the courses, right? So in this example, We could start from 1, but if the orders changes, we could start from 3, and then if in previous iterations we have already found that from 3, since there is no outgoing edges, so the maximum depth would be 1. And then after that, in other iterations, if we start from 1, since this one is already calculated and this is the only adjacent node to 1, so we can simply just, if we have cached this value, we don't have to continue the DFS from that node. So if the structure was like this, so let's say 1, 2, 3, and then 4, 5, and etc. It could be a very complex graph with lots of children, right? And computing this, running this DFS on all nodes will take a long time. But if we have cached this value somewhere in the cache that we could have access in O1, then after running the DFS from 1, we could simply use this value instead of running DFS again on node 3 and then add 1 plus 1 and then store it as a result for 1. So for that, I define the longest path, or L path for simplicity, is none for in branch n. So this is longest path value for each node, or maximum number of nodes starting from each node. So this is our cache. If the cache is none, that means it is not calculated yet, and we need to run the DFS on that node again. Otherwise, it is already calculated. What else I need here is to keep track of the not visited nodes, so that we know that we need to iterate through all n nodes. But in some cases, so if we start from 1, we are visiting 1, and then it has 1 edges, and we are also visiting 3. But we need to keep track of the all visited nodes, so that whenever this DFS finishes, we know that there are still some leftover nodes that haven't visited yet, and we also iterate through them and then visit them as well. So keep track of not visited nodes here. Not visited called a set of range of n. So we are simply just adding 0, 1, 2, and 3, and so on to n. And these are the edges that we have not visited them yet, and we just pick a random one from that and then run the DFS on that. So I want to define my DFS function here from starting node, or let's say start. Let's call it node. I will pass that here so that we first know what we are going to do. So while the length of not visited is greater than 0, so that means there is still some node that we have not visited yet, so we need to pop that from the list, from the set, sorry. And then the answer is equal to, we run the DFS on that node. We also need to keep track of the maximum value, so longest path. Initially it is 0, so on each iteration, longest path equal to the maximum of the longest path. And the answer, by running the DFS from that specific node that we just run, and then keep track of the maximum value every time. So the answer. And then after that, return the longest path. We have not discussed how to find the loop here as the example that we have here yet. So in the implementation, we will discuss that. But this is let's assume that for now, this graph doesn't have any cycle. So by starting from the node, if it is already computed, so that means we are storing the maximum path. This is our cache, right? So if L path for that node is not none, that means it has been visited. So simply just return LPass for that node without running the DFS again. So quickly just extract it from the cache. Otherwise, the current, let's say, is 1 because this is the maximum value starting from this node, but since the node itself counts as well, so we are starting from 1, and then for each children or for each adjacent, so starting from here it is 1, and we iterate through the running the DFS on all children's, and then each of them return a value. So this is the maximum value from children 1, children 2, children 3, children 4, and so on. We find the maximum value over them plus 1 with the answer, because it takes one semester to pass this course first and then the next one, and the maximum length from starting from the current node is the maximum value of the starting from each children node plus 1 for the current node. So for children, we have the graph here as an adjacent list in graph of the node. These are the list of children. If the node doesn't have any children, like the node 3 here, so it would be empty. So we are not iterating over anything. So let me pass again. And then after that, we update the cache. LPass of the node equal to current, and then return current. So we are restoring the value, the current, after iterating through all children's current, and then returning the current as a result as well. Otherwise, child or answer from children equals to the DFS of the children. So we are running the answer from the children, and then current equal to the maximum of the current and the answer from children plus 1, because it takes one semester to go from the current node that we are visiting here to the children. So keep track of the maximum value, and then after that we are running the DFS. So it is fine for graphs, directed graph that doesn't have any cycle. But in this problem specifically, we know that there might be a cycle in this graph. How can we detect them and then return -1 directly as soon as we find a cycle in the graph? So let's say we have a graph like this. This is the relations, and then we have there's some cycle like here. So let's say we first start from node 1, and then so we go through and then visit 2, and then visit 3, and visit 4, and visit 5. The first time that we should realize that there is let me change the color. There is a cycle is while we are visiting node 5, because it should be a label. 5 would realize that since we are going like a stack in DFS, 2 is already waiting for a get a response from 3, and then 3 is waiting for the response from 4, and etc. So 2 doesn't have any value yet. So the LPass for 2, is still none, right? Is still none, but we should remove them from the visited, the set of visited, as soon as we visit each node. So as soon as, whenever we are visiting the children, so we remove them from this visited list, so that as soon as node 5 realizes that it has a children, that it doesn't have any value, so it is not computed, but it is not also in visited. That means there should be some other node extracted this node 2 from the not visited set, and since it doesn't have any value yet, there must be a cycle in this graph, because it is still waiting for a response and hasn't gotten value yet. So here we can say if the LPath for children is none, and children not in not visited. It doesn't got any, it haven't got any value yet, and the children is not in not visited set. So we return -1. -1 means cycle detected. And then the cycle could be not from the current node, but from an answer coming from the children. Because if there is a cycle in the children, then children returns -1. We should realize it here. So before updating the maximum value, we check if less than 0, again return -1. And similarly here, if answer than 0, return -1. Return -1. There is a cycle in the graph. Likewise here. We should also remove, so whenever we know that after this node we want to visit this node, so we should somehow aware the children node, the rest of the nodes, that this node is already visited. So we are visiting the node. So whenever we are visiting each node, so let's say if, oh, not here. So whenever we are visiting a node, if node in not visited, let's remove that. No. So we are visiting, whenever we are visiting a node, as soon as the first time that DFS is called on some node, currently we are visiting the node, so we are removing that from the set. So let me run that for, okay, so it should be fine. I wanted to double check everything is fine here. So let's run the second example that does have a cycle. Oh, it was already this one. So let's run, or was it, oh, this is the example with the cycle. Okay, so let me submit that. There it is. So sometimes it runs faster, but sometimes it's slower. So I could run it in 300 milliseconds before recording this video. But this problem, we solved it by finding the longest path in a directed graph, having a cycle using DFS and caching. Hope you enjoyed this video.